Okay, welcome to Space Startup News Live. I do this live stream every week at the same time. So I normally just recap my videos I've done this week, typically 2 dedicated videos on a topic, then a roundup of space news. And I'll go over the comments people have left on the videos, quite a few comments this week. And yeah, you can chat, ask any question on any space topic, and we'll take it from there. And I'll end with any other space news that's happened and that didn't make the space news for any reason, and then a preview of what's happening next week or the week after, ideas I have for upcoming videos. So this week, I start with Etherflux. So put myself in the corner there. So this is a fairly small space startup that I've been aware of for a while, and I decided, okay, I'll cover it this week. So I've covered space-based solar power already. There's several companies I've talked about. Space Solar, a UK company, that's beaming megawatts of energy from space to Earth. I also covered Volta Space, which is will have satellites around the moon and beam power down to rovers on the surface. And there's some other companies in this field that I've not covered yet. There's some US companies as well. But this is a small company based in California, and it's operated by the CEO, if I bring him up here, is Badgie Bart, who was a co-founder of Robinhood. Place for private investors to, a website they can invest in finance and shares. But now he's running Etherflux. So basically, it's a small startup. There's I think 20 employees, and they have about $60 million in funding. They recently got 50 million, and they had 10 million before, so now it's 60 million. But the CEO is worth billions of dollars. It's a billionaire. So it's one of those space startups that's run and founded by a billionaire. There's quite a few of them now. There's Blue Origin, there's SpaceX, and relative to space is now, the CEO is Eric Schmidt, so he's a billionaire, and now we have Etherflux. So their company is collecting solar energy in space and beaming it down, but their system is quite small. Basically, they will have 100 satellites once they build the constellation, and it will use an infrared laser. So typically the other companies are using microwaves, which requires very large ground stations, hundreds of meters or even kilometers in length. That's not the case with Etherflux. You only need a 5 to 10 meter diameter dish, and you can collect power. So this is good for like forward operating bases, or there's been a disaster, you can just set up a dish. It could also be used on US Navy ships, and later on perhaps commercial ships. You just need it's a fairly big dish, 5 to 10 meters, but then you can receive power from space. So they have a mission in 2026. They've received the satellite already, so they're just integrating all the components and all that technology onto the satellite, and it will be able to beam 1 kilowatt of power down to Earth, down to a receiving station, and it will transmit power for 30 seconds to 60 seconds each pass over the ground station. So that's what they're trying to demonstrate in 2026. And Badgie Bart said that he wants to first zero in on the technology. So just work on one satellite to zero in on the technology, get the technology right first, and then they can scale up to the full constellation of satellites. So this seems to be a more practical way of doing space-based solar power, rather than requiring a kilometer length satellite with tens of thousands of solar panels that has to be assembled in space with robots. That's a giant project. For instance, Space Solar, that's their kind of that's their design. It's very, very large, which is great. You can beam hundreds of megawatts of energy down per satellite, but this is a much smaller scale operation and possibly more practical to begin with. You don't need as much capital. You can start with a single satellite to test the technology and then just scale up satellites. And there are many more use cases. Individual ships, I guess US Navy ships to begin with, could receive the power. Forward operating bases, which do struggle with energy. I say that in Iraq and Afghanistan, 3,000 US soldiers were killed in fuel convoys. You have to send these convoys to the forward operating bases, and it's very, very dangerous. So if you can beam power directly down to the base, it would be a much better solution. So I think there's plenty of use cases for this company. And, what they're trying to do is not a huge project. It's just start with a single satellite, just test the technology and scale from there. So it's a good idea. And there's a few comments on this. Marty the Martian says, small and scalable should make this startup more viable than those who are required to lift higher masses into orbit, not to mention the need for less area on the ground. Yeah, that's I think its advantage over the others is that it's much smaller scale, less capital is needed, less technology development, and there's more use cases. And Wingsley saying, nice video presentation. Let's hope that technology like this becomes fully operational and useful in powering our society. Space-based solar power is the future if we use our wits to recognize its potential and actually start doing it. It took us long enough, didn't it? Yeah, I mean, I think this is the future for power, generating power in space. You can beam it down to Earth. There's companies like Starcatcher that will beam it to other satellites. Volta Space is orbiting the moon, will orbit the moon and beam it down to equipment and rovers on the moon. So it's useful everywhere. So it's just a matter of starting the process of the technology, putting the satellites up there, testing them, and then scaling out. So you can either do it lots of small satellites or a few very large satellites. There's two different approaches. Both could work. So it's very interesting, and we'll see what happens with space-based solar power in general. And there's a few other companies I've not covered yet, which I may in the future. So let's move on to the second video this week. So I've been meaning to do a nuclear propulsion video for a while. And we have a comment. Adam is saying, have they selected a launch provider yet? Not that I'm aware of. I mean, yeah, I assume it's probably going to be Falcon 9, but who knows? The mission 1 is in 2026 for Etherflux. They're building the satellite at the moment, so yeah, we'll see how it goes. I'm sure there'll be updates on their progress. Yes, also the nuclear one, I've already done a nuclear video on NASA selecting a 100 kilowatt nuclear power station. That came from the US administration, basically saying China's building a nuclear power plant on the moon by 2035, so we need a nuclear power plant on the moon by 2030. So we now know there's going to be nuclear reactors in space, or at least on the surface of the moon. So given that, the next question is, I think, from a lot of people, is can we use nuclear power to propel spacecraft? And the answer is yes. So this video was looking at the two main methods of nuclear propulsion, and those are NTP and NEP. So NTP is nuclear thermal propulsion, and NEP is nuclear electric propulsion. So in both cases, you use a nuclear reactor to generate heat, and you can then use the heat to directly expel fuel, which is normally liquid hydrogen, at very high speed. Basically, the heat you generate is very high, it's thousands of degrees, and that will accelerate liquid hydrogen out at the end of the chamber through a nozzle at very, very high speed, and that propels you forward. So that's a very simple mechanism. The other is to generate electricity and then use the electricity to move the spacecraft forward using ion thrusters. So this is kind of like a concept of one. At the top bit, you have the nuclear reactor. Then the middle bit is the radiation shield. And then you have a long metal truss. And at the end, you have all your science equipment, your payload, whatever it is there. So that's basically what it looks like. Typically, there's various different ways of doing it. But so that is the two methods is nuclear thermal propulsion and nuclear electric propulsion. And I do mention in the video, this is a proposed trip to Mars and Ceres. It's 4.6 years. So I found this paper and I thought it was interesting. So they've worked out all the trajectories and so on. And apparently it's like 11.2 kilometers per second to get to Ceres, which with nuclear propulsion is quite possible. So basically, I go through how long it takes, but it's basically for 4.6 years to send 6 crew towards Mars, drop 3 of them off at Mars, then go on to Ceres. You should spend 46 days around Ceres, then come back to Mars, pick up the crew, and head back to Earth. So this is the kind of mission we can do once we have a functioning nuclear propulsion engine. One thing it's worth saying is that nuclear thermal propulsion is better for crewed missions because it has high thrust. That means you can quickly accelerate away from a planetary body from Earth orbit, and you can quickly decelerate to enter orbit around another planet. So for crew, it's better. Higher thrust is better for crew. Nuclear electric propulsion is very low thrust, but for a long time. So it's great for robotic missions. Basically, you have a lot of electrical power on board, which means you can power a lot of powerful scientific equipment, like maybe radar, or you could even run like big computer systems. You could have a data center. You've got hundreds of kilowatts of power, or maybe even megawatts of power. You could even run some kind of active magnetic shielding, rather than have heavy passive radiation shields. You could just have a magnetic shield. That's using nuclear electric propulsion. So you've got 2 different modes, propulsion modes. One's great for thrust, one's great for coasting and for generating a lot of electrical power. So yeah, those are the 2 methods. This graphic is from, if I can bring it up, there it is. This graphic is from, this is from the paper called Byers and Mal, which was a paper explaining how US keeps leadership in nuclear in space. So they looked at all the different proposals. They talked about generation 1, 2, and 3, and nuclear electric propulsion and nuclear thermal propulsion. And the different colors represent small scale, medium, and large scale. So basically, you start with power first. Can't bring myself here. Okay, you start with power first, and then once you've got a working nuclear reactor, say 100 kilowatts, you can then move on to nuclear propulsion. But you test out the system by just generating power first. So then you can do a nuclear reactor. You can handle the thermal management, the heat rejection. You've got the high power electronics. And once you've got all that figured and working on the moon, then it's just a matter of sticking an engine on the back. So that's bring myself up. So that's the kind of rationale. Start with power, validate it on the moon, and then it's just a question of adding a propulsion method. So you do one step at a time rather than trying to do everything at once. So I have this graphic, if I can bring it up here. So NASA is working on this 100 kilowatts. So that's 0.1 megawatt nuclear reactor for the moon, and that should be hopefully functioning by 2030, around about 2030. With one or two proposals, we'll see how many proposals are selected, but that's been fast-tracked now, so that's great. For fast transit to the Mars, you're going to need something a bit more powerful, something around 400 kilowatts. I don't know why this keeps showing up, because it shouldn't, but it should be this one here. Anyway, but it should be 400 kilowatts to 2 megawatts for fast transit to Mars, and this will require a Generation 2 nuclear reactor for fast transit to Mars. And for fast transit to the outer planets, you need something absolutely massive, 300 to 500 megawatts in power. That's because you have to get to the outer planets quickly. Basically, you want to get to a planet within 2 years, 1 or 2 years, because of the radiation exposure. Once you're traveling through space, you've got the solar flares, you've got occasional solar flares, and you've got constant galactic cosmic rays that are bombarding the spacecraft all the time. So you don't want to spend too long traveling to wherever you're going. So you will go to the outer planets. You're going to want to get there in like 1 or 2 years for Jupiter, maybe 4 or 5 years to Saturn. So you have to go really fast. So you need a really powerful nuclear reactor, which is hundreds of megawatts. For Mars, you need something smaller, 1 or 2 megawatts, maybe even half a megawatt will do. So that's why you can't really get to the outer planets with nuclear propulsion. You can't do a fast transit anyway without like Generation 3, Generation 4 nuclear reactor. It's fine for robotic missions. You can use nuclear electric propulsion, and you can spend 5, 10, 15 years, and you can send a lot of equipment, do a lot of science. Yes, so what else did I want to say about that? Yes, I had this graphic on here about active shielding. So NASA's looking at this, ESA's looking at this, and it's quite practical. We need something around 60 to 100 kilowatts to generate an active magnetic shield that will protect the crew and the spacecraft and its payload from solar rays and galactic cosmic rays. And yeah, so that seems doable if you're using something like nuclear electric propulsion. So anyway, that is my thoughts on nuclear propulsion. And NASA's looking into this now, so hopefully we'll have a lot more progress on nuclear reactors and nuclear power plants, and eventually nuclear propulsion. So if I bring up the comments, let's see now, if I can remove that. And can I put myself in the corner? No, I can't put myself in the corner. Let's remove that one here and remove that one. Okay, there I am. So quad rate demonstratum is saying 100 kilowatts equals 100 hair blow dryers, and leaping from planet to planet within our solar system on a reasonable time scale will take way more power than that, more like 1,000 gigawatts. But it's a really good idea, so let's get to work on it. And so there's a reply saying from Jessica, saying megawatt is sufficient for a small craft, and it is. Megawatt is fine for you can get to Mars with crew with megawatts, and megawatts is fine for robotic missions to the outer solar systems. Obviously, more power is better, but you don't need gigawatts. 100 kilowatt is fine for the moon's surface to begin with. There's some small habitats that will require less than 100 kilowatts, and you know, this is generation 1. You start with 100 kilowatts, and then you just scale it up. So I think starting with 100 kilowatts is fine, and we'll just scale it up to generation 2, generation 3. And Ed Hal 9000 is saying the main problem still being the particles ahead of the ship. At high speeds, they act as bullets that can perforate the hull and jeopardize the crew and equipment inside it. And Jessica replies, not at these speeds, and a simple composite shield will take care of micrometeorites. So yeah, I don't think there's any problem that the spacecraft is flying so fast that there will be problems with the shield. like I said, a nuclear electric propulsion is very, very gentle thrust. Over time, it can add up to a high speed, but I don't think there's any issues with speed at the moment. That would be a nice problem to have. And David Smith is saying, and we cannot let the NTP exhaust into Earth's atmosphere for radioactive reasons. And Jessica is saying, I can bring it up here, just remove myself. Jessica said, no, it's actually Tom Fraser saying, the heat from the nuclear power unit only heats the hydrogen. It does not make the hydrogen exhaust radioactive. Yeah, so there's no radiation at the exhaust. The radiation is inside the reactor, and it's used to just generate heat that expels hydrogen, just pure hydrogen, nothing else. So that's all the exhaust is, just hydrogen, no big deal. And Jessica makes a point, we can combine them both together, nuclear electric thermal propulsion. So I wasn't aware about this, but I did look it up, and there's some compelling reasons to combine NTP and NEP, because if you think about it, nuclear thermal propulsion is great for high thrust. It's great for accelerating away from a planet, doing a burn towards, like, from Earth to Mars, or being captured by a planet. So it's great for thrust. But nuclear electric propulsion is great for powering electrical equipment, your science payloads and so on. So you really want both. So you can have like one nuclear reactor with two modes, a high thrust mode and a cruise mode. So yeah, combining the two methods makes a lot of sense. And maybe that's a video in the future, because I kind of like the idea of exploring that a bit more. So if I remove myself and, okay, bring myself up here. And there's some more comments at the stage. Put myself down here. So Wayne is saying, silly question, but why hydrogen? It's a pain to store. Yeah, hydrogen is a pain to deal with, but there's a reason people try to make hydrogen work is because it's very lightweight. And Matt says it is low in mass, therefore easier to accelerate, which provide more specific impulse. Yeah, that's the answer. That's why people try to make hydrogen work, is because it gives you very, very high ISP. You look at all the chemical rockets that have the highest ISP, 400, 450 seconds, they're all liquid hydrogen, liquid oxygen. So, and it's the same with nuclear reactors. If you want to shoot something out of the engine really, really quickly, hydrogen's the best bet because it's so light. And here we have Jay Desta saying, chemical rockets are obsolete outside the moon's orbit, 250,000 miles. Yeah, I don't know about that, but definitely I think we should have nuclear propulsion at some point. Definitely for the outer planets, it makes a lot of sense. And for fast transit to Mars, it would also be very, very helpful. And also to power habitats on the moon and Mars. Crisis is saying, the euphemism heat management makes the enormous problems of heat dissipation in nuclear electric propulsion systems. This video doesn't do a good job of digging beneath the manufacturer's public relations brochures. Yeah, like, I didn't use any public relation brochures, but yeah, I mean, I could always deep dive into every piece of technology and every issue, but I don't want to deep dive that much. I kind of want to cover the whole subject more broadly. So yeah, there's places you can deep dive into the technology. Sure, there's definitely issues with heat management, with the radiators. There's issues with materials. Nuclear reactors get very hot, thousands of degrees, and the more powerful you make it, the hotter it's going to get, and the more difficult it is to find materials that can withstand the heat. So there's definitely lots of technical issues, but it's just a matter of like the progress. You know, start with 100 kilowatts, then scale it up, and then solve all the technical problems one by one. And Marty is saying, I hope these propulsion systems make people realize that Starship is not the right vehicle for Mars, but will be better utilized as a heavy lift vehicle to get projects like this into LEO. Yeah, there's various different ways of doing things. I think Elon's going chemical reactors chemical engines because they're available now. Nuclear propulsion isn't really available now. It's going to take 5, 10, 15 years to develop the technology, and he wants to get to Mars really quickly. But I think eventually nuclear propulsion will be the way we move around, certainly to the outer planets and to the asteroid belt and so on. And Lima Brava is saying, and we built and test nuclear thermal rocket engines from the early 60s and end of the 70s, and then tech was stuck on a shelf. Yeah, that's kind of the case with a lot of things in space. They get developed and then nothing happens. They don't get funded. This technology, nuclear technology has been around for a long, long time, 50 years, 60 years. But I think now maybe it will be developed. Hopefully NASA will fund 1 or 2 projects for a 100 kilowatt reactor, and then we'll just go from there. Then once it's been validated in space and on the surface of the moon, once we have the technology, I'm sure it will be used everywhere. It will be used on Mars, for asteroids, and for propulsion. It just makes a lot of sense, I think. And like I said, there's 2 different modes, propulsion modes. You've got high thrust, NTP, and you've got lots of electrical power, NEP. And in the future, you could combine them together to make it even better. So I think it's the future looks very good for nuclear propulsion, in my view, anyway. So if I can bring this up here. So I can bring myself here. So space startup news. So I covered a few topics this week. Nord Space, which is a Canadian space startup, and then Firefly Aerospace, and then I covered Rocket Lab. So Nord Space is launching. Was supposed to be this weekend. They had a technical issue, which has put it back. Their launch license has now expired, so they have to get a new launch license. But I think they'll be launching in September. So in a couple of weeks, their Tiger vehicle, which you can see here, it's a suborbital vehicle. It's liquid fueled, and it's using their, I think, Hadfield engines. So it's the very first liquid fueled private rocket engine to launch from Canada and from a commercial Canadian spaceport. So there's lots of firsts with Nord Space, and they're scaling up to their Tundra vehicle, which will be a orbital rocket, similar to Electron in that kind of scale. And it's all in-house technology. They developed everything themselves, so vertically integrated. They're moving very quickly, and they will be launching their first rocket very, very soon now. A couple of weeks, I think, because they need to reapply for their launch license. So hopefully there's no problems with that, and that happens very quickly. And let's move on then to Firefly Aerospace. So they've flown 6 times so far. Only 2 flights have been 100% successful, and so that success rate is 33%, which is not good at all, compared to like Rocket Lab, which is they've flown 70 times, and the success rate is 94%. So it's not looking good for Alpha Rocket, and Flight 6 was a failure. The FAA has cleared them to fly again. Apparently the angle of attack on a Flight 6 was a bit higher than normal, and it ended up rupturing the first stage, which the pressure wave then blew off the nozzle on the second stage, and it didn't have enough thrust to get to orbit. So the payload, which was a Lockheed Martin satellite, ended up in the Pacific Ocean, which was not good. But they think they know what the problem is. It's the angle of attack was too high, so they're just going to lower it back to what it was before, add some thermal protection, and hopefully Flight 7 will be a success. So Firefly Aerospace not doing that great on the rocket launches. The Blue Ghost lunar lander is doing great, 100% successful. They got a mission 2, 3, and 4 from NASA. So they've got the lunar lander. They've got some OTVs, space tugs are working on. They got the launcher, and they're also scaling up their launcher to remove that. They're scaling up their launcher to for a medium launch vehicle called Eclipse, and they're working with Northrop Grumman on this vehicle as well. So this will be a 16-ton payload to LEO, and I think this will also be able to send cargo to the International Space Station eventually. are commercial space stations. So there's quite a few companies now working on medium launch vehicles. You've got Rocket Lab, you've got Relativity Space, you've got Stoke Space. Now you've got Firefly with the Eclipse vehicle, and there's probably a few more that I've not even mentioned. So I think the medium launch vehicle market is going to get a lot more crowded. Right now, SpaceX just owns that market, and there's really no competition. I mean, you've got Ariane 6, you've got Japanese launcher, Indian launcher, but really the Chinese. But really, in the Western commercial market, other than SpaceX for medium launch vehicles, you've got ULA with a Vulcan Centaur, you've got Blue Origin's New Glenn. But yeah, the more launches, the better. So Eclipse is hopefully on the way, and we'll see how that goes. And the third story was Rocket Lab's now activated their Neutron launch pad. This is at Wallops Island in Virginia, and they've now built the launch pad. It took them about 2 years, and it's ready for the Neutron vehicle, which should be launching this year. It's very, very soon now. The launch pad's available. So you can't really see very clearly on this, but there's 2 launch pads here. If you look at the white water tank, that's where the Electron launches from, and the black water tank is the launch mount for Neutron, their medium launch vehicle, which can launch 13 tons to low Earth orbit, which will compete directly with SpaceX. SpaceX can lift 22 tons, but in practice, they never normally launch 22 tons commercially anyway. Their ride shares is usually 3 to 5 tons. So 13 tons is a direct competitor to SpaceX. I think the price is going to be similar, and it's partly reusable. The first stage comes back. The fairings, which are attached to the first stage, come back. So it's partly reusable. The second stage is expendable, but it should be a lot cheaper to operate, much higher launch capacity. So it is competitive with SpaceX, depending on the price, of course. Dave Huntsman, I don't have the comment here, but he had a really good comment on the video saying that he thinks Firefly Aerospace will struggle to compete with SpaceX because their costs will just be higher. He was reckoning 60 million as a cost, not a price, but the actual cost to Rocket Lab will be 60 million, and SpaceX's cost is probably around 15 million now. They charge a lot more, but it only costs them internally about 15 million. So he reckons Rocket Lab will find it quite difficult to compete with SpaceX. Well, I guess we'll see, right? I don't know. So that is the space news this week, and so let's talk about other space news. There's a few things here. ISA Aerospace, which is probably the leading European space startup that's trying to launch a rocket, is it's got its first privately funded player in Europe to sign commercial launch service agreement with ESA, the European Space Agency, and the European Commission. So they've got, I think, 2 contracts for our satellites in 2026. So this is the ISA Aerospace rocket called Spectrum launching. It only managed to last 30 seconds before failing and crashing, but at least it got off the launch pad, and the second vehicle is well on its way. I think the hardware's mostly built, so fingers crossed. The second flight does a lot better than the first flight, and there's some other companies as well, Rocket Factory Augsburg and so on. But yeah, they've got a contract from the European Space Agency and the European Commission, so that's great for them. And I also put this because I was talking about nuclear propulsion. China's long-term space exploration plans include a nuclear-powered probe to Neptune, launching in the 2040s. So China is working on nuclear power plants on the moon, and they're also working on nuclear-propelled spacecraft, robotic spacecraft. So, the West needs to be building these systems as well. And so that is nuclear. That is the other space news. So in terms of what I want to do next week. I've got a few things. I want to do a lunar infrastructure video. I'm building lunar roads and so on, because I think that's kind of force multiplier for everything that happens on the moon, for habitats and rovers and lunar ice harvesting. Having infrastructure such as roads and landing pads really helps. I also want to do. I have to find some new space startups. I've got a list of space startups, so I'm going to work my way through those. I also want to do maybe this combined nuclear thermal propulsion, nuclear electric propulsion video on combining them. There's some compelling reasons to do that. So I've got a few ideas, and we'll see what I come up with next week. So thank you for joining the live stream, and I do this same time every week. So please drop by if you've got the time, and I'll see you next week.